Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I'll help get you started with Class 25 on two-way categorical tables, or contingency tables, which aims to discover an association between two categorical variables. So in this assignment, we have a markdown file and a data file. So we'll need to download both of those to our classwork folder. And we'll start our studio, and we'll take a look at both the markdown file and the data file. This data file is not a CSV file or a comma-separated values file. It is space delimited, and so we'll need a slightly different function for reading that in. So I'm setting the working directory and knitting this file, but we'll also go and open the data file and take a look while that's knitting. All right, that finished up. So here is the data file. Okay, the first 40 or so lines have a description of the data set and a description of the variable names. If you want to look at the full data set, we're going to end up subsetting this data. And the data start at line 41. And notice that we don't have commas between the names here. Also, the strings are not in quotes. We just have spaces between each of the fields. All right, we've already knitted the document. Let's look at the HTML. So we're going to look at two different parts of the same data set in this assignment. We're going to look at whether goals are associated with the grade level, right? So as you get older through the grades, do your goals in terms of getting good grades, being popular, or playing sports, do those change? So is there an association between the grade level and your goals? Similarly, we'll repeat the analysis, but instead of grade level, we'll look at the school area. So do your grades, popularity, or sports relate to whether you are a rural student, suburban, or urban student? And you'll see at the end of the assignment why I've chosen to do this twice. So I'm calling this data set Popular Kids because popularity was one of the, these factors of grade, sports, looks, money, were ranked in terms of their popularity or their importance for your popularity. All right, so subjects were students in grades 4 through 6 from 3 school districts in Michigan, and the authors stratified their samples into 3 school districts, urban, suburban, and rural, having about a third of their sample from each of those districts. And students indicated whether good grades, athletic ability, or popularity was most important to them. And they also ranked other factors. Other information we got were gender, grade level, and other demographic information. And the full data set, you can look at the full data set in the DAT file. All right, so we load the tidyverse. We're going to read the data set in. So now instead of read_CSV, we're going to do read_delim, which is a delimited file where you specify the delimiter. In this case, the delimiter is a space. So we're going to read the DAT file in with a delimiter space, and we're going to skip the first 39 lines. Seems to me like we should be skipping the first, well, I've closed it now, the first 40 lines, but maybe we end up with, okay, anyway, we know that it works. We're also going to filter the areas to just these urban, rural, and suburban areas, in case there were others. And we're going to select the 3 variables we're interested in: goals, grades, and the area your school is in. Finally, all three of these are factor variables, and so we're going to mutate and turn them into factor variables. The summary of the data set gives us frequencies for categorical variables. So among the goals, most of these 4th through 6th graders thought grades were the most important, followed by being popular, and then sports were the least important. The grade levels, there were fewer 4th graders who participated compared to the 5th and 6th graders, and the areas are roughly equal, with slightly more students coming from the urban areas. Okay, so we are going to investigate these two questions: our goals associated with grade level and our goals associated with the school area. So you might take a moment and in your own head and think about whether you think one of these is more likely than the other to be significant, or if they're both, their associations are going to hold for both pairs. My own intuition says that while kids are changing pretty quickly between these grades, they're not going to change very much, especially if they're, say, in the same actual physical school building those 3 years. So I would say that probably it's unlikely that these goals are going to change very much over those 3 close years. Whereas, where your parents live and the types of lives that you have, depending on where you live, could probably change how important you think these things are: grades, popularity in schools, in sports. Okay, so our hypothesis test that we're looking at today is called a homogeneity of proportions, meaning are the proportions of students who rank grades, popularity, and sports as being important, are those proportions the same for rural students and the same for rural students compared to suburban students, and the same for urban students? That would be homogeneity, that we have the same proportions being represented for each of these school areas. Okay. By the way, the relationship that we're testing is not dependent on a direction of variable. In fact, it could be that the proportion of rural, suburban, and urban students who find grades important would be we're also testing whether that's the same as those relative proportions for students who say popular and those who say sports. So it goes both directions. Sometimes there's a natural direction to interpret. In this case, I think it's more natural to say within rural school districts or school area, what's the proportions of students who find these different goals important? So for me, I'm thinking about school area relating to goals. Similarly, I'm probably also doing grade level. Within the 4th grade, how does this distribution, what is the distribution of proportions, and how is that different for the 5th graders and the 6th graders? Sometimes you could interpret it both directions with equal ease. So this hypothesis is a little more complicated to state, but in words, we typically say the alternative hypothesis is that there is an association between one of the variables and the other variable, and it doesn't really matter which order you specify this in. The notation for this is more complex, and I recommend that you just follow this example, that the null hypothesis is that the probability that I and j are both true, meaning the ith category from a row and the jth category from a column, right? So it could be the 2nd row and the 3rd column, is equal to the product of the row probability for I and the column probability for j. And I go into more detail of this in the notes. Versus, at least, that this relationship does not hold true for all the row and columns. So it's false for at least one row and column category. Okay. So this is another way of saying that the probability of row category I conditional on column category J does not depend on which column category we consider. So the probability of I, for the row probability, conditional on J, is the same as the probability of I without conditioning on J. That is the same for every column. Okay. Always choose a significance level. We'll use 0.05 in our case. Compute a test statistic. We will compute the Chi-Square test statistic for this test. Compute a p-value for that, and the degrees of freedom depends on the number of rows and the number of columns. So if we've got 4, in this case I guess we've got 3 and 3. So 3 rows and 3 columns. So 3 minus 1 is 2, times 3 minus 1 is 2. 2 times 2 is 4. So we should have we should have 4 degrees of freedom for our tests. And depending on how our p-value compares to our alpha level, we either reject the null or fail to reject the null. And then we will also check the model assumptions for this. In this case, the expected count for every cell should be at least 5. If that's true, then you're in really good shape. There are cases when you've got sort of small tables, and there's been quite a bit of study on contingency tables and when we should, what assumptions we really need to trust the results. And I've got here that that the expected counts should be at least 1, provided that the expected counts are not too variable, meaning that we don't have a large expected value in one cell with small values in all the other cells. Right? If they're all sort of roughly uniform, then that could also work out for us. There are exact tests for this type of right, so we're using a Chi-Square test, which is an approximate test. There are exact tests, but they're very computationally intensive, and often the software to do the exact tests is expensive. All right, so that brings us to our first example. Goals versus grade level. Is there an association? So the first thing I do is, and I'm not going to use any of the tidyverse syntax. I find that for these tables, it's much easier just to use the R functions. But we'll start by summarizing the frequencies and the column proportions. You could also do row proportions. It doesn't matter. I'm doing column proportions for contextual reasons. The column proportions are interpreted as the proportion of students with each goal conditional on each grade. If these column proportions are roughly the same for each grade, then that's an indication that there's no association, that it doesn't matter which grade level you're in, the proportion of goals is the same. So X tabs, cross tabs, is the easiest way to get some frequencies. So we put in our data set, and we say we want summaries for goals. That's on the X or the row variable, and grade, which is the column variable. And I just want you to count up how many observations there are for every combination of goals and grades. And that we're putting into the table for goals and grades, and that looks like this. So for all the goals and all the grades, so there are 63 students in 4th grade who think grades are the most important goal. Okay, there's 31 who their goal is to be popular, and 25 it's all about sports. If you put that table into the prop table function, it calculates proportions for a table, and specify the margin. So margin equals 1 is by row, and margin 2 is by column. And if you had a higher dimensional table, you could specify a margin 3 or 4 or whatever. So for each column, I'm calculating the row proportions. So here for each column, these numbers 53, 26, 21 are adding up approximately to 1. Based on rounding, they may not add up exactly to 1. For example, these 6th graders, these numbers add up to 0.99, but that's due to rounding. It's without truncating this number or rounding this number, these numbers add up to 1. So looks like about half the people think that grades are the most important, with a slight advantage to popularity over sports for the distribution. And that's not too different over the 3 grade levels. Popularity seems to become a little more important for 5th and 6th graders, and sports and grades go down maybe a tiny bit. But these are such small differences that I hesitate really to interpret them at all, and certainly not strongly. So now let's go through the hypothesis test. And I've done some of the coding for you, so I don't give you points for every little step, but I do ask you to set up the null and alternative hypotheses, and I want you to sort of basically just fill in the alternative hypothesis. There is an association between the row variable and the column variable. The rest of this, in notation, I think you can leave it as it is, because it says what we need it to say. So that's not bad. You get a point for typing two words in there. A significance level of 0.05. We'll compute the Chi-Square statistic. So here's the Chi-Square test. We put in our table. That's this table here. That is our data. And using those frequencies, the Chi-Square function, the Chi-Square test function, is going to compute the Chi-Square statistic. We're not using a continuity correction. In practice, you probably want to, but in our case, I'd want this to correspond to the Pearson Chi-Square statistic that you could do by hand. I'm saving that in the Chi-Square GG. That GG is for goals and grade. And the result is that we have a Chi-Square statistic of 1.3 with a degree of freedom of 4 and a p-value that's quite large. Chi-Square statistics that are less than 4 or so are going to be pretty small. So our statistic is 1.31 with a p-value of 0.86, and I give you a point for stating the conclusion in terms of the problem. So you want to say that you either reject or fail to reject the null hypothesis based on the p-value's relationship to alpha, and then you want to say what that means, right? If you rejected the null, right, what is the null hypothesis? That there's no association between these row and column, then that's what you would say. There's no association between goals and grades. If you rejected the null, you would state your conclusion here, that there is an association between goals and grades. You haven't specified what that association is. You've simply identified that the association exists if you reject the null. Okay, so in our case, we have a fairly small p-value, or excuse me, a large p-value, and I'm going to let you fill in the blank. You know how to do this. All right. Finally, check the assumptions of the test. Right. So I've restated that here that the expected cell count for every cell should be at least 5. That's the best one to use if you have sufficient data. So within the Chi-Square object, right? So when we did the Chi-Square test, we had this Chi-Square object. There's a bunch of stuff in there. One of them is the expected counts. And so here are the expected counts in all these cells. This is under the null hypothesis that there's no association. And these are all large numbers. They're all at least 5. In fact, one quick way to test is ask for what is the minimum value. It's 22. Is that bigger than 5? Yes. So are the model assumptions met? Yes. Okay. So the cool part of a chi-square analysis is trying to understand, if you reject the null hypothesis, where those differences are. So if you reject the null hypothesis, the Pearson residuals are a way to indicate which cells of the table were different from expected. Residuals that are, roughly larger than 2 in magnitude are considered large and worth understanding better. So here in this chi-square object, I'm looking at the residuals, and I'm rounding just to 3 significant digits. That's to help us read the numbers better. If you get the 6 or 7 digit default, it's a little overwhelming. But you can see all these are less than 1 in magnitude. And so none of these residuals are very big. Recall how you calculate the, if I page up for a moment, the chi-square statistic is you can compute the residual and then square the residuals. Okay, so here I've squared all the residuals, and then you can add them up, and that gives us the chi-square statistic. So no real reason for me to do this here except pedagogically to show you that in fact we get the chi-square statistic. Okay, so here I want you to interpret the Pearson residuals. Basically, are there any that are more extreme than plus or minus 2? In this case, no. So there's really no interesting cells here. Basically, the data are consistent with the null hypothesis that there's no association between these two variables. Finally, we can plot those Pearson residuals, or plot the data and then overlay colors associated with the Pearson residuals, and that's what this Mosaic Plot does right here. It's a visual representation of the observed frequencies in terms of the area of each box, and the Pearson residual appears as color. And if the rectangles are roughly the same size across rows and across columns, so sort of the height of each of these bars, if those are roughly the same across each of these columns, then that's consistent with no association. And that's what we see here. The Pearson residuals on the color bar axis over here, everything is gray, and there's nothing interesting happening. And there's a p-value here consistent with the null hypothesis. So what was the rest of my paragraph here? Okay. Anyway, so I think I want you then to interpret the Mosaic Plot. And I think I've probably said enough to set you up for success there. Let's look what happens now in the second example when we look at these goals versus the school area. Are rural, suburban, and urban students different in terms of their goals? So we're going to do the same thing, except instead of grade, we have area. So I'm going to go pretty quickly through this because it's largely a repeat of what we just did. Here are the data, and what do we see? So the rural students sort of almost equally split. Suburban students, grades are much more important than the others. Same thing for urban students, possibly even more so. So let's look at those proportions, and yeah, so basically the same story. In fact, suburban and urban are they basically give us the same proportions to 2 decimal places for the data set. Okay, cool. So it looks here like maybe there's going to be some differences. Rural students have a larger emphasis on sports and popularity and less importance on grades compared to their urban and suburban counterparts. Okay, so we got the same, you can do the hypotheses. We go through, we perform our chi-square test. We have a chi-square value now of 18 and a p-value that reflects some difference here. I want you to state the conclusion, check the model assumptions. So here's all the expected values. Okay, you'll be able to assess that. The smallest of the expected values is 28. Let's look at the deviation details. So here we've got residuals that are a little more interesting. So here we see a -2, and for the rural grades, and for rural sports we have a positive 2.6. Everything else is less than 2. Yeah, and you can see, for example, like in the grades row, the rural has a negative value, whereas suburban and urban are both positive. So there's sort of the contrast, right? Rural is different than suburban and urban. Same thing for sports. Sports is positive for rural, but negative for suburban and urban. And sort of these values for popularity is sort of close enough to zero, maybe not to worry too much about it. The residuals squared, these are the contributions to the Chi-Square statistic, right? And if you add all those squared values up, you get the Chi-Square statistic of 18.8. Okay, so I want you to interpret those Pearson residuals as I just discussed there. Let's take a look at the plot. Okay, so now we've got sort of a plot that's interesting to look at. Where is, sorry. Looks like did I produce the same plot twice by accident? Yours will not have both of these in there. Okay, I'll just have this one where I've added the title. So first thing to look at is the areas, right? In fact, sort of, right, to my eyes, I see the color first, so I immediately want to interpret the color. So I guess let's start there. The Pearson residuals, the blue values are Chi-Square statistics greater than +2, and the red values are less than -2. Okay, so the blue cell is larger than you'd expect by chance if there was no association. And the red one is smaller than you'd expect by chance if there was no association between area and goals. Okay, but we've in this case we've concluded that in fact there is an association. So then we can go on to look at this table. So right, the areas of these, each of these cells represents the frequency or the number of students in every pair, right? So the number of urban students who valued grades is this upper right gray box. And you can see the suburban and urban students are basically exactly the same in terms of their goals. And it's the rural students who are really different. They value grades less, they value sports more. And what about popularity? So these gray cells are pretty close to each other, right? Their popularity is a little more important for rural students, but not right. This difference is not big enough really to get excited about it statistically. There seems to be a small difference, but the real big differences are sports. Sports looks like it's almost twice as important for rural students. In grades, maybe a third less important or something. So I want you to interpret this plot. So this is a really straightforward assignment, and I hope it went easily for you.